All right, well, let's start this last session of the Revercomb Symposium. The first talk is by Joe Taylor. Joe Taylor is a research engineer at the Space Science and Engineering Center, University of Wisconsin-Madison. He received his BE and master's degrees in engineering physics from the University of Saskatchewan and his PhD at the Center for Optics, Photonics, and Lasers at the University Laval with Hank Revercomb and Jerome Genest as co-advisors. Joe is one of our honorary Canadians. Oh, that doesn't say that here. Joe came to SSEC in 2003 after first meeting the UW-SSC SS team at Safari 2000 deployment in South Africa 3 years earlier, something Dan Laporte mentioned yesterday, or earlier today. He is key member of the SSEC's infrared high spectral resolution remote sensing group led by Hank and the engineering research and development group led by Fred Best. Joe's research interests include design, optimization, analysis, and high accuracy calibration of infrared Fourier transform spectrometer systems, infrared optical system design and analysis, and infrared detector performance evaluation, optimization, and nonlinearity correction. His talk title is The IR Absolute Radiance Interferometer, ARI, Prototype for CLARREO, Part 1, Overview and Performance. Joe?
Thanks, Bob. Well, good afternoon. We're down to the final three, I guess, here. As Bob mentioned and Dan mentioned yesterday, met this group, Hank's SS group in 2000. It's a Safari 2000 deployment. And I remember coming back from that deployment, and this was a big aircraft deployment, one of the old Mike King affairs with teams from JPL, from Ames, all over the US, and then lots of ground stations in the UW group. And I remember coming back and telling my wife Ange immediately after coming back, is you should have seen this UW group. They're fantastic. You know, if I was going to go anywhere, that'd be it out of those groups there. And lo and behold, a couple years later on a Friday night, my group at University of Saskatchewan, my director was moving to Hawaii to assume the directorship role of the JCMT telescope. They're dissolving our group, and I got a phone call from Dan Laporte on Friday night at my home asking if I was looking for work, which was a lovely coincidence and a life-changing opportunity. So after a trip down here to visit people and convince them that it would be a good hire, I started here in 2003. Hank has been an incredible mentor, colleague, and friend to me in that time. You know, we've all got these similar statements about Hank, you know, the words that reoccur. Words such as mentor, colleague, friend, optimist, persistence. My experience, his intuition is unmatched. I keep telling him that. I don't think I've ever won a beer from him in a bet. So if he tells you something about an instrument, it's usually true. He has an energetic curiosity that is extremely rare, and it's fantastic. And he treats everyone and everything with respect and interest. It doesn't matter who you are or what you're doing. It's the same level of interest and respect. And you have to work very hard, I think, for a person to lose that. He's one of those people that sees the good in everybody. So I'm looking forward to many more years here working with Hank and the group here. It's such a great group of people. So it's been a wonderful opportunity. So from there, I'll move on to my talk. And nowadays at a university institution, you rarely get to build an instrument. So this was one of those wonderful opportunities. We're building an instrument for the CLARREO prototype, and then you get to build it with these people, so that's an extremely rare occurrence. So I've got some of those people listed here from the Space Science and Engineering Center, OMM, Harvard University, and then my co-advisor from Laval. I was a late bloomer, so my PhD topic was this project as well. Worked out nicely. And Fred's going to follow this up with a part 2 on the on-orbit verification and test system. I'm going to start with a brief introduction, and then I'm going to move on to the instrument, talk about its status, the demonstrated performance after testing, and then just finish up with a brief conclusion. In terms of the introduction, I'll talk a little bit about CLARREO. Hank touched on it yesterday. a history that's sort of IR and UW SSEC focused, a little bit about the ISS Pathfinder efforts at the time, and a few other topics in there. To start with CLARREO, it was originally a decadal survey, Tier 1 mission from the 2007 decadal survey. It was highly recommended. This was an effort that Hank and Jim Anderson at Harvard really led getting us into the survey, felt it was of great importance. It's basically a 3-instrument suite. You've got an IR, a reflected solar, and a GPS occultation instrument, and it's really a metrology lab on orbit. And it's for climate benchmarking and for system intercal with other satellite instruments. In terms of the infrared, the requirements for the measurement requirements are 1/10 of a Kelvin accuracy, and that has to be proven on orbit. So you take your national lab with you to orbit in the systems that Fred's going to present. In terms of the benchmarking the Earth's climate, these are spectral resolved measurements, and it's analogous to basically marking a glacier's current extent. We put a pin in the measurement. We don't need continuous overlapping records between satellites because it is absolute accuracy. It was originally envisioned that we'd have 5-year missions repeated every 10 to 15 years. And then perhaps just as importantly, it acts as an intercalibration standard because we have all these great sounders up there now that have 2/10, 3/10, 4/10 of a Kelvin accuracy. We cross-calibrate them with an absolute standard, and it plays into allowing us to get those years that we've been up there without the standard, work back and provide better coverage for time of day and whatnot. We talked about how we've gone from 10s of Kelvin to 10ths of Kelvin over the years, and it's an order of magnitude advancement over the past filter radiometers. And these current sounders, we're talking 2/10, 3/10 of a Kelvin, very valuable instruments. And that really comes from accurate spectral response function knowledge, or instrument line state knowledge in case of the spectrometer, the Fourier transform spectrometer. This is very important for forecast model assimilation and climate applications. And the ARI uses this advantage in on-orbit standards to offer new absolute reference for intercal and climate trending. I've pinched a slide from Hank here, and this is showing the old way of doing things. We've talked about this a bit in the last couple of days, and this was the right way to do things at the time. It was an accurate way, but it's a broadband measurement. And the first meteorological satellite that observed the Earth was from here, Vern Sumi and Robert Parent. Omnidirectional spheres, 3-color, black, white, and gold. And it's a spectrally integrated observation, which they continue to do today. From that, we've talked about over the last couple of days how we moved to spectrally resolved measurements, and in particular, the Fourier transform spectrometer that was worked on here, the colleagues of Hank and Bill Smith, whatnot, 1978 through 85, designed a high spectral resolution instrument for sounding temperature and water vapor from GEO, and that led to the HIS instrument, which we've talked about. A couple pictures of that aircraft there, the old U-2 from NASA, inside the Dewar on the HIS, which I understand was very difficult to deal with at times, being helium cooled in the field, and then a picture of the instrument in the bottom. So this was getting your feet wet and learning the virtues of the high spectral resolution measurements for improving absolute accuracy. Your uncertainties down to 10ths of degrees, even at this time. And this is, there's a paper by Goody and Haskins that talks about the importance of the spectral resolved radiances for calibration accuracy. From there, we move to the scanning HIS, and scanning HIS is similar to the HIS, same sort of coverage, 580 to 3000 wave numbers. We'll see this as a similar coverage to CLARREO without the far IR, half a wave number spectral sampling, and again, another instrument from ABB BOMEM. We've got the guts of the interferometer shown there with the infrared light paths. And then we look here, it's been on 5 missions over 20 years, 5 different aircraft. It's been quite a workhorse, and in addition to all the applications you see here, its most recent focus, sort of since the early 2000s, has been calibration validation, and Tom Pagano mentioned this as well. And AIR's nadir underflight here by SSEC on the ER2 on the 21st of November 2002 was actually the first ever calibration validation of spectral resolved radiance from space using a high altitude aircraft instrument. This is the work of Dave Tobin here. He's using the double obs minus calc. He's got a paper from 2006, and it's a technique that we use again and again and again. You can see the excellent agreement here where we're talking tenths of a Kelvin agreement between the aircraft and the satellite instrument once we account for the difference in viewing angle and whatnot. As an example of what we do when we don't have CLARREO up there is this CalVal approach with the high altitude aircraft. One of our most recent ones, we got to go to Iceland for flights over the Greenland ice sheet. They completed 7 ER2 flights. This was in 2015. So they're flying underflights under SUMI MPP, MEDOP A and B, as well as EOS Aqua. And the scanning his in this role has a clear calibration traceability to NIST, not only via its black bodies, which we've cross-calibrated with NIST references, but an end-to-end calibration that we can do in the compared to these absolute standards. So just a couple examples there of why we went into the field for this. You know, we've got these sounders that are extremely accurate. At warm scenes, they're almost on top of each other for the simultaneous nadir overpasses. But as we go to colder scenes, you're seeing sort of 0.3 of a Kelvin difference, which isn't big, but it's enough. So this was kind of taking a microscope into the field to look at those differences and try and pinpoint them. And this is what we came out with. Hank showed this slide yesterday. This is just a raw long wave window comparison from 850, 900 wave numbers of differences from spaceborne sensor to scanning is for CRIS, EASI A, EASI B, and AIRS. And you can see we don't really have this trend that we saw in the previous slide, so it requires a little bit of further digging. See what we're getting to there. Maybe it's polarization, maybe it's scan angle dependence, things like that. But this is a piece of the puzzle, and then this is just an example of the double ops minus calc as I applied it based on Dave's work for that mission. So you can see down here, this is the long wave CRIS to scanning his, where you're, you know, sub-tenth of a Kelvin difference between the two with full radiometric uncertainty assessment. So we can go from that. It's still a valuable method. It provides us this microscope of looking at a given time and place and condition with the aircraft instrument. But you know, having something on orbit allows us to have this absolute standard comparison with the statistical advantage of having it on orbit. So many comparisons with the other satellites. You've got the climate benchmarking aspect of it, and it provides a great deal of advantages. So we have a plot here from Bruce Weilicki, and it's basically the trend uncertainty. So your climate trend uncertainty on the y-axis and your time to detect in years on the x-axis. And it shows basically as your instrument measurement becomes more accurate, it takes less time to detect the climate trend. So we have EASI, AIRS, and CRIS, sort of their, this is actually a K equals 2 or 2 error here, and they're in here, and it looks like it's, so you can see their lines coming from here. So I've selected a 1/10 of a Kelvin uncertainty, drew the line across. So it's taken about 40 years to detect at that uncertainty, whereas we get to the CLARREO instrument with that accuracy, so a factor of 2 times shorter to detect. How do we get a more accurate instrument, given how well built these sounders are? Well, this instrument is built with the climate benchmark measurement and the intercalibration problem as its primary role. We don't need contiguous coverage. We don't need cross-track coverage. We can emphasize linearity over noise and polarization, for example. We only doing nadir sampling, so we can put the black bodies and the reference standard and the Earth view at the zero crossing points of the polarization. So it allows us to beat down this uncertainty because we're restricting really what the requirements are. And most of the people that work with instruments here know the requirements do not add up linearly. They multiply, so the cost and complexity goes up in a hurry. And this is not necessarily a new development. It's been going on for years. People have been pushing for this. As slide from Hank, so 1993, ClimeSat with Jim Hansen. Again, 3 instruments, very similar to CLARREO. You have the Michelson interferometer, Mint is a familiar name to Henry Buys probably, but not for this instrument. And you've got the visible and a polarimeter in this case. So 2 spacecraft for adequate sampling. And they relied, because they didn't have the absolute accuracy, they relied on continuous observation, so overlap between multiple launches in time. And then we had Jim Anderson at Harvard with the Arrhenius proposal, and this is very much like the nation of CLARREO that made it into the decadal survey, and that actually evolved into the ASIC study in 2005 that Hank and Dave Tobin and other people in the room here were greatly involved in. So where are we now? 2008, 2010, after the decadal survey, NASA said, yes, they gave the responsibility to NASA Langley. Science team was formed. The IR and RS instruments were decided to be developed under instrument incubator program. So UW and Harvard were doing the IR, and LASP was doing the reflected solar. 2011, bad news. We've heard of a recurring theme over the last 2 days. It's bad news, bad news, bad news, good news, bad news, good news. So it comes and goes. So 2011, funding profile was removed for CLARREO, so it was basically canceled at that time, except they were allowed to have some pre-phase A studies continue to go on from 2011. 2012 to 2014, we're finishing up our IIP work. We achieved a technology readiness level of 6, which is critical to move forward in other programs for space flight at the UW and Harvard, as well as at LASP for our instruments. And then to 2013, they started working on the Pathfinder concept, which is a space station demonstration of this instrument. This is just a conceptual view of it here. Much of the same value, you get sort of a minus 52 to 52 latitude coverage, but you can cross-calibrate with the current sounders to get the rest of the coverage, and it is still a very, very valuable reference. We had the good news, 2016. The budget suddenly had money for the Pathfinder. It sort of came out of nowhere for many of us, but it was followed up by bad news again, where NASA looked at their funding budget that they put over to propose to this and decided they didn't have enough money for both instruments, and they decided to go with reflected solar to begin with, and then would try and find funding for the IR later. Looking at the ARI, this is the CLARREO coverage, so your standard sounder, 600 to 3,000 here, and then we cover out to 200 wave numbers, captures the far IR. And in terms of measurement uncertainty, our goal here is 1/10 of a Kelvin, 3 sigma, or K equals 3. And when you combine a sampling uncertainty of 1/10 of a Kelvin, you get an absolute accuracy combined of 1/10 of a Kelvin, K equals 2. So this is the requirement in the black, and then this is the on-orbit prediction, given all our uncertainty contributions for the calibration in the dark lines and the verification in dashed. Picture of the instrument here, just looking at the optics from the side view and the top view overlaid on a SolidWorks rendering. It's a 4-port interferometer, heart of the system, a flight heritage design from ABB. It's a large aperture, so 10-centimeter aperture, cesium iodide beam splitter here. You have 2 output ports, one with uncooled far IR, so noisy, but it does have coverage out to 200 wave numbers, and then a cooled, probably 2 or 3 channel detector system at the other one. This is just a picture of the as-built system there, and Fred's going to be talking about this side of the system, and I will focus on this side, the FTS. It's not unlike any of our other sounders. We calibrate the scene by looking at space and looking at an onboard ambient black body, and that allows us to calibrate that Earth scene radiance. It does have these other technologies that Fred will get into in his talk, and so we have a on-orbit reference standard. We have what we call the OCMs, which are emissivity modules, and then we do line shape measurements on orbit. And this is effectively that carrying your laboratory with you to space. For the instrument status and demonstrated performance, we did vacuum testing in the SSEC with a borrowed chamber from physics. So we get some pictures of the guys working on it here. Doug Adler, Jeff Wong, Denny Hackle, and these pictures here getting it into the chamber. And then here's the system in the chamber. This is basically a plot of observation in red on the right here. So we're looking at the uncooled detector and the prediction in black. So on this side, we've got plus or minus half a Kelvin. This is a long time period of data averaged. You can see the DTGS is quite noisy, so to look at the residual I've binned in terms of spectral bins here. We do have a low signal and noise effect that is due to an unoptimized beam splitter coding at the long wave end of the far and at a little bit here as well. But in general, for the rest of the band, we are within the 1/10 of a Kelvin on orbit spec with this result. This is the cooled MCT long wave detector. So this is much less noisy, so you don't get as much hash here. You can see we're going again 117 Kelvin to 333 Kelvin, so the full range of scene temperatures. And this is again is plus or minus 0.5 Kelvin on the left, and the residuals on the right. Good residuals here within that plus or minus 1/10 of a Kelvin. But we noticed we had something going on at this edge of the band that we didn't quite expect. So we spent a lot of time diagnosing that and doing some post-vacuum testing. Found it to be a stray light issue at the field stop. So we didn't have time to go back into vacuum, time or money to go back into vacuum, but we did some dry air purge collects from 243 Kelvin through 333. And you can see this fix. Things actually look a lot more flat as well. And the only feature you have here is the CO2 band here, 15 micron CO2 band, but you look at the residuals, how clean they are within this plus or minus 1/10 of a Kelvin over the full range of scene temperatures here. And a similar thing for the far IR. So get a little more noise. It's not expected to be an issue in orbit because we do a lot of averaging for the far IR for the climate product, and it's not cross-calibrating any instrument because it would be the first far IR resolved spectral measurements of the Earth probably since the 70s, I believe. So. Our current work, we're integrating a QCL, quantum cascade laser, that was developed under the IIP into the system. Fred's going to talk about that integration process a little bit more. I'll talk a little bit about what we're doing with it. So our first thing was to bore sight it with a Heaney so we could tell where we're pointing. So we did that with magnetic locking kinematic bases. It's a combination of custom and COTS mechanical elements. Bore sighted from 10 to 180 centimeters. So you have the Viz picture on the left and the infrared picture on the right when we're going through this verification process. And then I can use that Heaney laser, look at direct injection into the cavity for this OCHEM measurement, so the emissivity measurement, and I was interested in seeing what the variation was with position and distance from the apex of the body. So we pick the position with the Heaney in, and then we switch it out for the QCL. You get basically a line shape superimposed on a black body. And then we repeat that measurement for a range of positions across the apex, and we get sort of the expected curve we thought we'd see here. And this allows us to know what the sensitivity is to the positioning of the laser within the cavity. Second part of the direct injection testing is looking at the ILS, comparing that to CO2 laser results, making sure the QCL is actually monochromatic. And again, good results there. We get a reasonable line shape. Things are looking good. We've got one more step to repeat on this, and then we're going to move into the flight-like configuration where we inject it off the scene select mirror, and Fred's going to talk about that a bit. So in terms of this project, I mean, it was really fun to go through this and get hands-on hardware, work through this from the start to the finish, and design through assembly and testing. Standard metrology methods were used throughout because we really are trying to be a standards lab in orbit. To assess radiometric uncertainty for the instrument calibration and on-orbit calibration validation systems for the laboratory, vacuum, and on-orbit environments, because each present their own difficulties and uncertainties. We tested it end-to-end under vacuum and the expected on-orbit thermal environment, and were granted a TRL of 6 by NASA ESTO, the Earth Science Technology Office, and have shown that we have the ability to achieve the required 1/10 of a Kelvin at 99% confidence on orbit accuracy required for the climate benchmarking measurement for CLARREO. Extensive characterization of the system was done, including nonlinearity polarization, this effect that some of you may be familiar with. This goes up to Von Walden and Penny Rowe, a low signal to noise effect. So we developed a new version of the Revercomb equation to deal with that. Miniature phase change cell performance, which Fred will talk about. And this really was a successful demonstration of the enabling technologies for the CLARREO infrared system, and it was accomplished with an instrument that has a short path to a flight instrument. So we have components that have high TRL and direct flight heritage. We're hoping that the ISS moves forward for the IR. It gives us a risk reduction, but it also gives us a chance to improve the overall accuracy of our operational sounders out there. As Hank said, it's not a vote, so having an absolute standard there, we can compare each of them to that standard, and then we can leverage those sounders to start a global benchmark record. Good news, the Reflected Solar Pathfinder effort is underway. Not so good news, the IR Pathfinder we're still waiting to see how we can figure that one out, and the full mission remains in extended pre-phase A. Just finish up with a couple pictures here, Hank, and thank you very much for several good years and hopefully more to come. So thank you.
We have time for some questions for Joe.
That's good.
I'm going to wait for one.
You got 2 minutes. No, Tom's got one.
Can you describe a little bit more about the effect you saw where at cold scene temperatures you did see a calibration error, but you didn't see it under other conditions that were also cold scene temperature? Because we're seeing something like that on airs.
Yeah, so it did show up. It was most obvious looking at a cold target. And I think we even saw it when we had a cold target with a cold body. And so I think it was partially because that's where we were most sensitive to the stray light effect. And it was a field stop effect. So I don't know if I made it clear, but we saw it in the MCT side, but we didn't see it as much in the DTG side. It wasn't as obvious. Part of that was because of the noise, but part of that was because they had different aft optic systems as well. So there's probably a little stray light advantage or at the field stop area for the DTGS. We weren't seeing that.
I think the question was, when you showed the comparison with Chris and Aaron.
You're talking Chris and Ayers or the, okay, I thought you were talking about the ARI.
But you didn't see it with the aircraft?
Yeah, so the first thing, so like you, I've been working on polarization for Chris, where you've been working on polarization for Ayers. I'd be interested to see simultaneous nadir overpass, so it should be, you know, for Chris, in the long wave, the polarization error isn't necessarily at its least at the nadir view. So we may be seeing an effect of that. So I'd like to do some simultaneous off nadir comparisons, see if we can see that. I mean, that's a little bit of a harder thing to do, but that would be my first inclination, probably just because I've been working on it a whole bunch, so it's on my mind. But I think that would be the first thing that I'd want to look at now that we've got out there with the aircraft and didn't see this effect. A difference, you know, the 0.3 of a Kelvin difference between the instruments. The aircraft stuff's wonderful, but for being able to get a close-up on this, but we don't have the statistics either, so I may be looking at, you know, we've got, you know, a dozen cases there. We may have some that aren't representative of what's statistically normal for persons too. These are pretty tough flight conditions, mostly clear scenes, but some that were quite dynamic, so to be very careful in the comparison. But my first thing to look at would be the polarization and see if we had some angular dependence based on the scene mirror angles between the different instruments.